This is Module 14, the Transport Layer, for the Introduction to Networks version 7.0 curriculum of the Cisco Networking Academy. The Transport Layer is responsible for the logical communication between applications running on different hosts. The link between the application layer and the lower layers that are responsible for network transmission. As you can see from the TCP/IP model, the application feeds through the transport layer to the internet layer, while the internet layer feeds through the transport to the application layer. In the OSI model, the transport layer is the only layer that is named the same as in the TCP/IP model and performs the same function. The transport layer has the following responsibilities. It tracks individual conversations. It segments data and reassembles segments. In an earlier chapter, we discussed TCP. And TCP sets up sequence numbers so that data can be reassembled if it arrives at the destination out of order. UDP does not do this and must rely on upper layer protocols to tell it to resend data so that it does arrive in the appropriate order. At the transport layer, we would add a header information about the type of data or port number that we are transporting. We would identify, separate, and manage multiple conversations. And it uses segmentation and multiplexing to enable different communication conversations to be interleaved on the same network. As we can see here, I have opened up 6 screens, all going to the same product on eBay. How does the computer keep each one of these conversations separate? That is done through port numbers and sequence numbers, so that no matter which one I click on, the sequence numbers would tell the system that that is the page I want to work with. IP does not specify how the delivery or transportation of the packets take place. If you may recall, IP is a connectionless, unreliable protocol. The transport layer protocols specify how to transfer the messages between hosts and are therefore responsible for managing the reliability requirements of a conversation. When we talk about reliability, we are mainly talking about the TCP protocol. The two most common are TCP and UDP. Two terms that you may recall work with the TCP protocol are to maintain the fact that we have a complete connection, and it is the ability for reliability and retransmission. So whenever you hear the terms of reliability or retransmission, they would talk about the TCP protocol. As you can see in the diagram, some applications use TCP, some use UDP, and some, such as DNS, have the ability to use both. TCP provides reliability and flow control, as just mentioned. Some of the basic operations: they number and track data segments transmitted to a specific host from a specific application. They would acknowledge the received data. They will retransmit any unacknowledged data after a certain amount of time. The sequence data that might arrive in the wrong order can therefore be reassembled. And they will send data at an efficient rate that is acceptable by the receiver by controlling the window size. When a network becomes congested, we can adapt the window size so that the sending systems cut back the amount of data that they are sending. One process used is weighted random early detection, whereas when we approach the maximum threshold, we will randomly drop packets, and TCP, through its processes, will cut back the amount that it is sending. We can therefore do traffic shaping and traffic policing. UDP provides the basic functions for delivering datagrams between the appropriate applications with very little overhead or data checking. Whereas TCP is a connection-oriented protocol, UDP is connectionless. UDP is known as a best effort delivery protocol because there is no acknowledgement that the data is received at the destination. UDP is normally used for voice over IP because of the lack of overhead, making it much faster, which is necessary in either video or voice transmission. Because there is the possibility that packets may arrive out of order, we normally combine voice over IP using UDP with reliable transport protocol to give us sequence numbers. Therefore, if something arrives at the destination out of order, it can be dropped. It is not put into a voice or a video out of place. As we can see here, UDP is also used by request and reply applications where the data is minimal and retransmission can be done quickly, such as DNS or voice. If it is important that all the data arrives and that it can be processed in its proper sequence, TCP is the protocol of choice. TCP will first establish a session. TCP is a connection-oriented protocol that negotiates and establishes a permanent connection or session between source and destination devices prior to forwarding any traffic. We do a three-way handshake where the sending system will first contact the receiving system with a synchronizing packet. In this synchronizing packet, a starting sequence number will appear. The receiving system will reply with a synchronizing acknowledgement, in which it will have its own beginning sequence number and the sequence number provided by the first host plus 1. When that is sent back, the first host can then respond with an acknowledgement with the second host's sequence number plus 1. Now the two sides are synchronized and transmission can commence. Because of the sequence numbers, this ensures reliable delivery. For many reasons, it is possible for a segment to become corrupted or lost completely as it is transmitted over the network. Many things may affect this. Storms, electrical problems, many others. TCP ensures that each segment that is sent by the source arrives at the destination. It will also provide same order delivery. Because of the sequence numbers, the packets can be put back in order. Because networks may provide multiple routes that can have different transmission rates, data can arrive in the wrong order. But due to the sequence numbering, these can be reordered at the destination. It also supports flow control, as mentioned earlier. When a network host has limited resources, memory or processing power, or when TCP is aware that these resources are overtaxed, it can request that the sending application reduce the rate of data flow. This is normally referred to as the window size. In the TCP header, we can see it is a stateful protocol, which means it keeps track of the state of the communication session. TCP records which information it has sent and which information has been acknowledged. As we can see in the diagram, we have the source port as well as the destination port, the sequence numbers, the acknowledgement numbers, a header length, a reserve field, control bits, the window size, a checksum to make sure nothing has been corrupted, any urgent pointers, and any additional options if necessary. As you can see, the header is 20 bytes. The source port is a 16-bit field used to identify the source application by port numbers. Port numbers could go all the way to 65,535. The destination port must also be a 16-bit field due to the size of the number. A sequence number is a 32-bit field. With 32 bits, the number can be well into the millions. An acknowledgement number is also 32 bits so that we can acknowledge the sequence numbers of packets we have received. The header length is a 4-bit field known as the data offset, and this indicates the length of the TCP header segment. We have a reserved field, and this has been reserved for future use. We have control bits, and this may include codes, flags, or other types of control for the proper delivery. The window size is a 16-bit field used to indicate the number of bytes that can be accepted at one time. A checksum field used for error checking, and an urgent field used to indicate the contained data is urgent. Some of the applications that would use TCP are HTTP, FTP, SMTP, and SSH. These are only a few of many protocols that would use TCP to transport data. All these protocols need the ability of TCP in providing reliability, data flow, and reordering of segments. UDP is much scaled down. Data is reconstructed in the order that it is received. So if data is not received in the same order that it was sent, the file is corrupted. UDP relies on upper layers of the application layer to request that the data be resent. Any segments that are lost are not resent. We do not establish a session. and there is the sending of information and the replies, we have no way to inform one another about resource availability. We just send the data. So that this means there is no window size. So the data is just continually sent, and it either arrives or it does not. The UDP header, as we can see here, in comparison with the TCP header, the TCP header being 20 bytes, while the UDP header is only 8 bytes. So for every packet of the millions of packets that may be sent during a conversation, 12 bytes are saved. This is a large time saving and necessary for voice or video conversations. Here you'll notice we have a source and destination port, we have a length and a checksum, and that is all. The source port is a 16-bit field, as we found in TCP, as well as the destination port. The length is a 16-bit field that indicates the length of the UDP datagram's header. The checksum is also a 16-bit field used for error checking of the datagram header and data. Applications that would use UDP include DHCP, DNS, SNMP, TFTP, voice over IP, or video conferencing. Live video and multimedia applications. These applications can tolerate some data loss, but require little or no delay. Simple request and reply applications, such as DNS, DHCP. Applications with simple transactions where a host sends a request and may or may not receive a reply. Applications that can handle reliability themselves. Unidirectional communications where flow control, error detection, acknowledgments, and error recovery is not required or can be handled by the application. SNMP, Simple Network Management Protocol, and TFTP, Trivial File Transport Protocol, are two examples. Port numbers are critical so that the sending system and the receiving system understands what we are trying to do. TCP and UDP transport layer protocols use port numbers to manage multiple simultaneous conversations. The source port number is associated with the originating application on the local host, whereas the destination port number is associated with the destination application on the remote host. In most cases, if we are the originating requesting host, the destination port will be either a well-known port or a registered port. So we can tell the receiving system what we want to do, such as port 80 for web traffic. The source port may normally be a dynamic port greater than 48,000. When the receiving system replies, it would reply with our source port as its destination port and its destination port, the original destination port, as its source port. So in the reply message, the source and destination ports are switched. This way, the receiving system understands what we are trying to do, makes a reply, and the originating system recognizes what conversation it is meant for. Each of our request would have a different source port, so that in the reply messages, the computer system would know what request door the information was meant to go to, just as in the example of having 6 open sessions of eBay. The combination of the source IP and the source port, along with the destination IP and the destination port, make up what we refer to as a socket pair. The source and destination ports are replaced or are placed within the segment. The segments are then encapsulated within an IP packet. The packets are then encapsulated within a frame. The combination of the source IP address and the source port number, or the destination IP address and the destination port number, is known as a socket. The sockets enable multiple processes running on a client, and it allows them to distinguish themselves from each other and multiple connections to a server process to be distinguished from one another. As was discussed in an earlier chapter, well-known ports are those with a port range of 0 to 1023. And these port numbers, which are controlled by IANA, are reserved for common or popular services and applications such as web browsers, email clients, remote access. They define well-known ports for common server applications, enables clients to easily identify the associated service requirement. Registered ports are ports that have been assigned by IANA to requesting entity or companies to use within a specific process or application, such as real audio or real video. Upon development of these protocols, a request would have been made to IANA for port numbers, and these would have been built into the protocol. Cisco, for example, has registered port 1812 for its radius server authentication process. Above 49,151, starting at 49,152, to the maximum of 65,535, these are private or dynamic ports. These ports are also known as ephemeral ports. The client's operating system usually assigns these port numbers dynamically when a connection to a service is initiated. When we initiate a conversation, we would use either a well-known or a registered port as the destination and a private or dynamic port as the source. These are some of the more common well-known ports. 20 being FTP, 21 being FTP control, 22 as secure shell, 23 as telnet, 25 as SMTP, 110 as post office protocol, 443 as HTTPS. Using the netstat command, unexplained TCP connections can pose a major security threat. Netstat is an important tool to verify these connections. Using the netstat command, we can see the local address and port number and what is the foreign address and protocol that we are trying to accomplish, such as in the diagram, NetBIOS HTTP, you'll also see that the state is established because these are all TCP connections and because it goes through the three-step or process of handshaking. It establishes a connection. A UDP connection would not be established because we just send out the data. But TCP, through the three-way handshake process, establishes a connection with the receiver before the transmission of data, whereas UDP would just send it out, not knowing if the recipient is there. Here, you can see the TCP server process. So each application process running on a server is configured to use a port number. In a later part of the Cisco curriculum, we can see how to use access control lists to block particular services that we may not want to have running on our system. An individual server cannot have two services assigned to the same port number within the same transport layer services. An active server application assigned to a specific port is considered open, which means that the transport layer accepts and processes segments addressed to that port. This is one of the things that threat actors may try to find. What ports have been left open inadvertently, which leaves a receiving system vulnerable. Any incoming client request addressed to the correct socket is accepted and the data is passed to the server application. Here is an example of the three-way handshake of TCP. The initiating client requests a client-to-server communication session with the server. This is a synchronizing request. As we can see here in the example, computer A or host A sends a synchronizing request with a sequence number of 100. The receiving system, host B, sends a synchronizing acknowledge reply, giving it its beginning sequence number of 300 and acknowledging a sequence number of 100 plus 1, the next one it expects to get from A. A then sends an acknowledgement packet back with the sequence number initiated by B plus 1, which would be the next one A expects to get as a return from B. When the client has no more data to send in the stream, it sends a segment with the finish flag set. The server, or in our case, host B, acknowledges receipt of the finish flag. It then will send its own finish flag. A will respond that it has received B's finish flag, and the conversation ends. The function of the three-way handshake is multifold. It establishes that the destination device is present on the network first. You may recall that IP is a connectionless protocol. TCP is used to guarantee the connecting device is there and willing to establish communication. It verifies that the destination device has an active service and is accepting requests on the destination port number that the initiating client intends to use. It informs the destination device that the source client intends to establish a communication session on that port number. After the communication is completed, the sessions are closed, and the connection is therefore terminated. The connection and session mechanism enable TCP reliability function. One type of an attack from a threat actor would be to send multiple synchronizing packets. Because the receiving host will reserve resources, the number of packets that it can reserve resources, or the number of conversations that it could reserve resources for, is therefore limited. A threat actor will try to do a denial of service by sending these synchronizing packets to exhaust all the resources of the receiving system. Some of the control flags of the 6 control bits are urgent, so an urgent pointer field significant; acknowledgement, the acknowledgement flag used in connection with establishment and session termination; a push function, a reset function. The reset function will reset the connection when an error or timeout occurs; the synchronizing sequence numbers used in connection establishment; and the finish flag, where no more data from the sender and is used to terminate the session. Reliability and flow control is necessary. Although we may send packets out sequentially, they may not arrive at the destination in the same order. TCP can also help maintain the flow of packets so that the devices do not become overwhelmed. There may be times when TCP segments do not arrive at their destination, or they arrive out of order. All the data must be received, and the data in these segments must be reassembled into the original order. The sequence numbers are assigned in the header of each packet to achieve that goal. No matter how well we design a network, data loss occurs. In this example, TCP provides a method of managing these segment losses. And among these methods, the mechanism to retransmit segments for unacknowledged packet. Two terms for TCP would be positive acknowledgement and retransmission. Flow control is also used when discussing TCP, as well as reliability. As we can see here, segments 3 and 4 did not arrive. B can therefore request that 3 be resent through the acknowledgement. But as you can see, we will resend 3 through 10, which is also a waste of our resources because we are retransmitting segments 5 through 10, which were already received, duplicating information. We have the ability to request only the ones lost to be sent. Host operating systems today typically employ an optional TCP feature called Selective Acknowledgement, or SAC. This is negotiated during the three-way handshake. If both hosts can support SAC, the receiver can explicitly acknowledge which segments or bytes were received including any discontinuous segments. As we can see here, we acknowledge 3 and SAC 5 through 10. So now, instead of repeating segments 5 through 10 and wasting bandwidth, we move immediately to 11 and 12, as well as repeating the 3 and 4. TCP also provides the window size, or flow control, and this is the amount of data that a destination can receive and process reliability. This is negotiated at first and has to do with the amount of memory and processing power the receiving system may have. Flow control helps maintain the reliability of TCP transmission by adjusting the rate of data flow between the source and destination for any given session. As we can see here, we set a window size of 10,000. Once I stop with a sequence number of 1,460 bytes, or a window size of 1,460 bytes, we would send that as one group. We would send another group, after which we acknowledge that we have received the 2,920. So you may see our acknowledgement numbers are not increasing by just 1. They would be increasing by the window size or the number of bytes received. MSS is the maximum segment size, and this is the maximum amount of data that the destination device can receive. As we can see here, although the window size is 10,000, the MSS is 1,460. So a common MSS is 1,460 bytes when using IPv4. A host determines the value of its MSS field by subtracting the IP and TCP headers from the Ethernet maximum transmission, in this case 1,500 bytes. 1,500 minus 40, 20 bytes for the IPv4 header, 20 bytes for the TCP header, would leave 1,460 bytes of actual transmitted data in each packet. Flow control is used so that when congestion occurs on a network, it results in packets being discarded by the overloaded router. To avoid and control the congestion, TCP employs several congestion handling mechanisms, timers, and algorithms. UDP has very low overhead, but we sacrifice reliability. We do not establish a connection. UDP provides low overhead data transport because it has a small datagram header and no network management traffic. UDP does not track any type of sequence numbers the way TCP does. As in the diagram, if things are either lost or arrive out of order, there is no way to put these back into the correct order or to ask for the resending of datagrams that were lost. So it has no way to reorder the datagrams into their transmission order. UDP will simply reassemble the data in the order that it was received and forwards it to the application. Because the data will be out of order, the application will notice that the information is corrupt and ask for it to be resent. UDP-based server applications are assigned well-known or registered port numbers. And UDP will also receive a datagram destined for one of those ports. It forwards the application data to the appropriate application based on its port number. Just like with TCP, open ports could be a danger and a security risk to a system. If a particular protocol is not going to be used, the port number should not be allowed. The UDP client process dynamically selects a port number from the range of port numbers and uses this as the source port for the conversation. The destination port is usually a well-known or registered port, just as in TCP. After a client has selected the source and destination port, the same pair of ports are used in the header of all datagrams in the transaction. The source and destination coming from client 1 to the server will be the opposite source and destination that the server will respond back to client 1. The same happens for client 2. This concludes Chapter 14, the transport layer.